The word submarine comes from the Latin prefix sub, meaning under, and marinus, meaning of the sea. In English, it appeared in the 1640s to describe something located or operating underwater. The first ideas for underwater vessels emerged back in the 16th century. English mathematician William Bourne created drawings of a fish-shaped vessel. It was supposed to submerge by filling its ballast tanks with water and surface by emptying them. However, a prototype was never built. In 1620, Dutch inventor Cornelius Drebbel created the first known navigable underwater vessel. It was a wooden rowboat covered in greased leather for waterproofing. It was propelled by oars passing through flexible seals, and fresh air came in through tubes running to the surface. The boat was tested on the River Thames with the support of King James I of England. Drebbel's vessel held up to 16 passengers and remained submerged for up to 3 hours. It covered several miles at a depth of 12 to 15 feet, refreshing the air using a system of bellows connected to the tubes. By 1624, Drebbel had built at least 2 improved versions. He proved the feasibility of underwater travel using muscle power. However, they were limited by the physical endurance of the oarsmen and the risk of the tubes getting clogged. A major step in the 18th century was the Turtle. It was a single-seat underwater vessel designed by American inventor David Bushnell in 1775, which was used during the Revolutionary War. It was shaped like an acorn and made of oak, reinforced with iron bands. The Turtle submerged using manual ballast tanks that filled with water and surfaced thanks to a screw pump. Propulsion was provided by a hand-cranked propeller. On September 7, 1776, operator Ezra Lee tried to attach a barrel of explosives with a clockwork mechanism to the hull of the British warship Eagle in New York Harbor. This became the first documented use of a combat underwater vessel. The mission failed due to mechanical issues and the inability to attach the mine. These early prototypes relied entirely on human power for propulsion and depth control. Submerging was achieved through ballast control or manual mechanisms, but they were severely limited by their air supply. Dives typically lasted only 30 minutes, after which the crew faced a lack of oxygen and the buildup of carbon dioxide. These limitations and the heavy physical strain on the operators only allowed for short dives to a shallow depth near the surface. The transition from muscle-powered prototypes to mechanically powered submarines in the 19th century was a key breakthrough in underwater navigation. This increased their reliability and paved the way for military applications. American inventor Robert Fulton designed and built the Nautilus between 1800 and 1801. It was a copper-sheathed submarine about 21 feet long. It had a hand-cranked propeller and a collapsible mast with sails for moving while surfaced. The vessel was successfully tested on the Seine River in France. Fulton and his crew submerged to a depth of about 25 feet. The Nautilus proved the possibility of staying submerged for a long time, but Napoleon Bonaparte ultimately rejected it. He doubted its practicality and considered the cost too high compared to the surface fleet. Although Fulton failed to secure funding, his work influenced future designs. It showed that submarines needed better engines and more efficient ventilation systems. During the American Civil War, Confederate forces built the H.L. Hunley. It was a 40-foot iron submarine completed in 1863. It was propelled by a screw propeller manually cranked by a crew of 8. On February 17, 1864, the H.L. Hunley carried out the first successful submarine attack in history. Off the coast of South Carolina, it struck the hull of the Union sloop USS Housatonic with a spar torpedo, causing the enemy vessel to sink in a matter of minutes. However, shortly after surfacing to signal its success, the H.L. Hunley vanished along with its entire crew. Examination of the wreckage shows that the sailors most likely died from the blast wave of their own torpedo or from asphyxiation during the mission. Meanwhile, in Russia, inventor Ivan Fyodorovich Alexandrovsky developed his own submarine. It was laid down in September 1864, launched in June 1865, and fully completed in May 1866. It ran on a pneumatic engine, marking one of the first steps toward mechanical systems instead of manual power. Late 19th century innovations built upon earlier ideas such as David Bushnell's submersible turtle from 1775. Designers improved hull shapes, buoyancy control systems, and observation devices, making the boats more reliable. Irish-American inventor John Philip Holland advanced these ideas in his boat Plunger, launched in 1897. It featured electric motors for submerged running, allowing it to reach a submerged speed of 7 knots, as well as an early version of a periscope for safely observing the surface. Despite initial stability issues, the battery system of the Plunger was an important step toward reliable electric propulsion. However, its capabilities were limited, with the charge lasting only 1 to 2 hours at a low speed. In the early 20th century, the introduction of diesel-electric systems solved the problem of surfaced range, while keeping electric motors for stealthy submerged operations. The German U-1, commissioned in 1906, became the first U-boat of the Imperial Navy. It had a 200 horsepower kerosene engine for a surface speed of 10.8 knots, as well as electric batteries for a submerged speed of 6.5 knots. However, due to its small size, its patrol time was limited to just a few days. Similarly, the United States Navy submarine USS Skipjack, launched in 1911 and commissioned in 1912, used diesel engines on the surface and relied on lead-acid batteries when submerged. It could only reach a submerged speed of 4 knots and operated for up to 1 hour, after which it had to surface to recharge. This significant limitation relegated the role of early submarines to coastal defense. These vessels laid the groundwork for fleet development and proved the potential of submarines during World War I, despite ongoing problems with battery capacity and air supplies. During World War I, German U-boats conducted a devastating campaign against Allied shipping. They sank around 5,000 merchant ships, striking a severe blow to supply lines. The campaign escalated sharply on February 1, 1917, with the start of unrestricted submarine warfare. This allowed attacks on any enemy and neutral ships without warning, aiming to place Britain under an economic blockade. This policy led to the loss of over 12 million tons of shipping in the final 2 years of the war. But at the same time, it provoked the United States of America into entering the conflict. To counter the U-boat threat, the Allies implemented convoy systems starting in mid-1917. They grouped merchant ships under escort protection, which drastically reduced losses by limiting opportunities for submarine attacks. Convoys proved highly effective. Sinkings dropped from a peak of 860,000 tons per month in April 1917 to under 300,000 tons by late 1917. U-boats struggled against coordinated defenses, including depth charges and hydrophone detections. During the interwar period, the 1922 Washington Naval Treaty imposed significant restrictions on submarine construction to prevent a naval arms race. It limited individual submarines to a maximum standard displacement of 2,000 tons and capped the total submarine tonnage for major powers. The United States was limited to 52,700 tons and Britain to 70,000 tons. These limits encouraged designs focused on efficiency rather than size, influencing models like the United States S-Class and the British Odin class. Despite the constraints, technological progress continued, especially in battery technology. Improvements in lead-acid cell designs increased energy density and submerged endurance. For instance, German Type 7 prototypes in 1930s achieved up to 80 nautical miles at a submerged speed of 4 knots, compared to just 50 miles in World War I models. Hydrophone advancements also marked the era. Passive listening devices evolved from World War I directional arrays to more sensitive towed and hull-mounted systems. This allowed earlier detection of surface vessels at ranges up to 6 miles in quiet conditions. Nations like Britain and the United States experimented with early active sonar prototypes. A prime example is the 1920s ASDIC system, which used ultrasonic pulses to locate submarines, laying the groundwork for wartime applications. World War II saw submarine warfare reach entirely new scales of production and tactical influence. Germany constructed 1,156 U-boat, including over 700 Type 7 boats. However, 784 were lost in action, and approximately 28,000 sailors perished in the campaign. The U-boat Wolfpack strategy initially ravaged Atlantic convoys, but Allied code-breaking of the Enigma machine through ultra-intelligence proved decisive. By Black May of 1943, 41 U-boat were sunk in a single month. This contributed to over 70% of German submarine losses that year, as decrypted signals allowed for preemptive ambushes. In the Pacific, United States submarines played a pivotal role in strangling Japanese logistics. They sank 55% of the enemy merchant fleet tonnage, totaling over 5,300,000 tons across 1,392 vessels, despite making up only 1.6% of naval personnel. The Gato class, commissioned starting in 1941, exemplified mass-produced effectiveness. It featured 6 forward and 4 aft 21-inch torpedo tubes, carrying 24 Mark 14 torpedoes for extended patrols. These submarines accounted for numerous high-value targets, like tankers and troop transports. Japan responded with innovative but limited designs, such as the I-400 class submarine aircraft carriers. These massive vessels displaced 6,560 tons submerged and could launch 3 Aichi M6A Saran float planes for reconnaissance or strikes. However, only 3 were completed before the war ended. These developments highlighted the shift of submarines from auxiliary vessels to true strategic weapons, setting the stage for post-war nuclear innovations. The advent of nuclear propulsion was a true revolution in submarine development during the Cold War. This gave them unprecedented submerged endurance and new strategic capabilities. The United States launched the world's first nuclear submarine, Nautilus, on January 21, 1954. On September 30th of that same year, it officially entered the fleet in Groton, Connecticut. Thanks to this innovation, Nautilus no longer needed to surface frequently to recharge batteries or refuel. Its submerged time was limited only by food supplies for the crew and maintenance needs. Nuclear power transformed submarines from tactical coastal defense vessels into a global strategic weapon, making them faster and stealthier during long patrols. The standoff between the United States and the Soviet Union intensified the underwater competition. Both superpowers raced to build the latest nuclear attack submarines. In 1958, the Soviet Union commissioned its first November-class nuclear attack submarine. That same year, the lead boat of the series, K-3 Leninsky Komsomol, entered service. In response, in the early 1960s, the U.S. Navy introduced the Permit-class submarines, also known as the Thresher class. They were designed for deep water combat against enemy submarines and could travel submerged at high speed for long periods. These boats became a prime example of the era's focus on noise reduction technologies and multi-role use. The introduction of submarine-launched ballistic missiles further strengthened nuclear deterrence. On July 20, 1960, the American Polaris A-1 missile was successfully launched underwater for the first time from the submarine George Washington. This marked the beginning of the sea-based leg of the nuclear triad. Several major incidents highlighted the high risks and complexity of service during that period. On May 22, 1968, an American Permit-class submarine named Scorpion sank southwest of the Azores. All 99 crew members were lost. Its wreckage was later found at a depth of over 11,000 feet. The boat was crushed by water pressure, likely due to a severe mechanical failure. Later, the crisis surrounding the Able Archer exercise in 1983 showed how easily submarines could trigger a global escalation. During the NATO exercise that simulated a nuclear conflict, Soviet ballistic missile submarines were placed on high alert because the Soviet Union feared a real preemptive strike. After the Cold War ended, technologies continued to improve for various missions and operations in coastal waters. On July 19, 1997, the lead Seawolf-class submarine entered the American fleet. It received advanced noise reduction systems, a state-of-the-art sonar, and powerful weapons to counter quiet Soviet submarines like the Akula class. The subsequent Virginia class, whose lead boat entered service in 2004, was built with an emphasis on a cost-effective modular design. The open architecture allowed the vessel to be quickly upgraded and to use commercial off-the-shelf components for intelligence, surveillance, and strike missions. Non-nuclear submarines also took a step forward thanks to air-independent propulsion systems. For example, the German Type 21-2 class, which entered service in 2002, used a hydrogen fuel cell engine. This significantly increased submerged endurance and made these export submarines even stealthier. Submarines move underwater by changing their buoyancy. This process is governed by Archimedes' principle, which states that the buoyant force acting on a submerged body equals the weight of the fluid displaced by that body. Mathematically, this means the buoyant force equals the density of the surrounding water multiplied by the volume of water the submarine displaces and the acceleration of gravity. For a submarine to stay on the surface, its overall density must be less than the density of seawater. This creates positive buoyancy. To submerge, the density of the boat is increased until it equals or exceeds the density of the water. This achieves neutral or negative buoyancy. The main mechanism for controlling buoyancy is the main ballast tanks. These are large compartments outside the pressure hull that are filled with water or blown with air. To submerge, valves at the top of the tanks are opened. Compressed air escapes, and pressurized seawater enters through openings at the bottom. The submarine gets heavier and goes underwater. To surface, the valves are closed and compressed air is blown into the tanks at 15 pounds per square inch from air banks where the pressure reaches 4,500 pounds per square inch. The air forces the water out and the boat rises to the surface. In modern submarines, the reserve buoyancy is between 12 and 15%. In an emergency, air is supplied directly, bypassing the pressure regulators, which allows the boat to surface very quickly. Maintaining trim, which is the balance between the bow and the stern, is vital for running level. For this, they use special trim tanks connected by pumps. By pumping water between the compartments, the crew shifts the center of gravity. This helps compensate for changes in weight, like when fuel or stores are used up, and keeps the submarine from pitching too far forward or backward. Transverse stability is maintained by evenly distributing water in auxiliary tanks on the port and starboard sides. In case of a breakdown, there is always a backup pump. Diving starts by flooding the ballast tanks. At the same time, the stern dive planes are angled so the bow drops a few degrees and the boat smoothly heads down to its diving depth. At the desired depth, the crew sets neutral buoyancy using the depth control tanks. They flood or pump out small volumes of water, sometimes around 21 long tons, to perfectly balance the weight of the submarine. From then on, depth is maintained using the dive planes on the conning tower and the stern. At high speed, the stern planes are used more often. The maximum diving depth depends on the strength of the pressure hull. If it is exceeded, the pressure will simply crush the submarine. For example, American World War II submarines had an operating depth of 250 to 400 feet. But calculations showed that the hull would fail and collapse at a depth of 500 to 600 feet. The density of seawater constantly changes depending on its salinity and temperature, so the balance has to be adjusted. Colder or saltier water is more dense, which pushes the submarine up harder and makes it seem lighter. To keep from surfacing, the crew has to take on extra ballast. Conversely, when entering warmer or less salty water, the boat gets heavier and water must be pumped out of the tanks. These adjustments are especially important in areas with sudden changes in temperature or salinity. There, the balance of the submarine can suddenly shift by several long tons, and without a quick reaction from the crew, the vessel could lose its desired depth. Submarine hydrodynamics depends on how the hull interacts with the water. Water resistance heavily impacts speed, efficiency, and stealth. This drag mainly consists of skin friction, which comes from water rubbing against the hull, and form drag, caused by pressure differences as water flows around the boat. Skin friction goes up if the surface gets rough from marine growth or corrosion. In temperate waters, this can add 0.125% to the drag every day. Form drag is highest at the bow and lowest at the streamlined stern. There is a specific drag coefficient used to measure total drag. For perfectly streamlined shapes, this coefficient can be as low as 0.01, while for standard cylinders, it reaches 0.6. Modern submarines use a teardrop hull. It features a rounded bow and a tapered stern. The length to beam ratio is about 7.5. This design cuts down both types of drag. When surfaced, it also reduces wave-making resistance. A great example is the United States Navy submarine USS Albacore. Its drag coefficient was 0.1, whereas older cigar-shaped boats had a coefficient of 0.35. Underwater, the Albacore could reach a submerged speed of 33 knots. Even though diving starts by changing buoyancy, hydrodynamics dictates the movement while submerged. Special control surfaces allow for precise maneuvering. The bow and stern planes control the pitch of the boat. Bow planes help at low speeds, below 3 to 4 knots, while stern planes take over at higher speeds. Planes on the conning tower provide extra control and reduce noise radiating forward. The rudders at the stern handle turning. The effectiveness of these surfaces depends on their area, the speed of the submarine, and their angle of attack. They are often arranged in a cross or X shape for reliability. The latter option improves handling by 40%. Placing the conning tower at about 0.62 of the hull length adds stability, but it can create water vortices that disrupt the stern planes if the conning tower is shifted too far back. Maneuverability is measured by the turning radius. This is usually between 2.5 and 4.6 times the length of the hull. At a speed of 10 knots, for a submarine that is 262 to 328 feet long, the turning radius will be 656 to 1,640 feet. At high speeds, propeller cavitation occurs. This is the formation and collapsing of vapor bubbles due to low pressure. It creates a loud noise, adding 10 to 15 decibels. This gives the submarine away since sonar easily picks up these sounds. To avoid this, the blade shape is optimized, but cavitation remains a problem at speeds over 15 to 20 knots. When submerged, submarine stability is a delicate balance between two states, static and dynamic. Static stability depends on the metacentric height, meaning the distance between the center of gravity and the metacenter. In submarines, this distance is small, about 1.3 feet, to avoid violent rolling, but it is enough to keep the boat balanced. However, once moving, dynamic stability comes into play. This changes based on speed and ocean currents. The hydrodynamic pressure on the conning tower during turns or when surfacing can overpower the static equilibrium. If the submarine rolls more than 20 or 30 degrees, it can lose stability. At high speed and in underwater currents, controlling the boat becomes much harder, which is why automatic systems are needed to hold a precise course. The heart of any submarine is its pressure hull. This is a strong, watertight cylindrical capsule designed to withstand the crushing pressure at great depths. It's usually built from high-strength steel alloys like HY80 or HY100. These materials can handle immense loads, from 80,000 to 100,000 pounds per square inch. This extreme strength allows the walls to be thinner without risking hull collapse. The cylindrical shape itself perfectly distributes water pressure, while hemispherical or conical ends make the structure even more reliable. Submarines are built using either a single hull or a double hull design. American submarines typically have a single hull that comes into direct contact with the water, with the ballast tanks built right into it. Soviet and Russian submarines more often have two hulls. The outer light hull, made of thinner steel or composite materials, improves streamlining and protects the inner pressure hull where the crew lives. This provides more interior space but increases the overall weight. A typical attack submarine measures about 328 feet long and 33 feet in diameter. When surfaced, it sits very low, rising less than 16 feet above the waves. Because of this, it's extremely hard to spot on radar or with the naked eye. Over time, materials improved to make submarines lighter and quieter. In 1971, the Soviet Union commissioned the Alpha-class submarines. For their pressure hull, they used the VT6 titanium alloy. Its density is about 281 pounds per cubic foot, which is almost half that of steel. This made these boats faster and more maneuverable. However, welding titanium was an extremely difficult and expensive process, and the metal itself required special protection against saltwater corrosion. Today, modern submarines are covered with special rubber or polymer tiles. This sound-absorbing coating has tiny voids that absorb sonar waves, making the submarine almost invisible to enemy detection systems. To save the crew in case of an emergency, the pressure hull is divided into several watertight compartments. Modern single-hull submarines might have only 2 compartments, while older models or double-hull submarines have 10 or more. If the hull is breached, these bulkheads stop the water and prevent it from flooding the entire vessel, preserving buoyancy. These internal walls are often made curved so they can withstand immense pressure from both sides. They work together with the main ballast tanks, helping the submarine to submerge smoothly or surface instantly in emergency situations. Submarine propulsion systems provide the energy for moving underwater. They have to strike a balance between speed, endurance, and stealth. The most common configurations run on electric motors that use stored energy, and the methods of generating that energy determine the operational limits. Diesel-electric plants, which are widely used on classic submarines, use diesel engines to charge batteries on the surface. When submerged, these batteries power the electric motors. This setup allows for a submerged speed of 5 to 10 knots on battery power and a surface speed of up to 20 knots when running directly on diesels. The efficiency of diesel engines in this case is around 35%. To increase the time spent underwater without surfacing, a snorkel is used. In its modern form, this system was developed by Germany during World War II. It features a retractable mast that supplies air for the diesel engines at periscope depth. This allows the batteries to be charged while remaining almost completely submerged. This invention, which the Dutch began researching back in the 1940s, significantly improved the endurance of diesel-electric submarines in shallow waters. Air-independent propulsion systems solve the problem of relying on batteries. They generate power without needing atmospheric air, which allows for much longer submerged patrols. Fuel cell systems, like those on German Type 21 submarines, use hydrogen and oxygen to generate electricity electrochemically. They reach up to 70% efficiency and allow patrols lasting several weeks. Stirling engines found on Swedish Gotland-class submarines run on a closed cycle using liquid oxygen and diesel fuel. They provide quiet, air-independent power for equally high endurance. Besides that, some modern conventional submarines, like the Japanese Taige class that entered service in 2022, have started using lithium-ion batteries. They have a higher energy density than lead-acid batteries, charge faster, and deliver submerged operating times that rival traditional air-independent systems. Plus, they eliminate the need for extra equipment. Nuclear power plants are the backbone of attack submarines in the leading navies of the world. They use pressurized water reactors to create steam. The steam turns turbines that drive the electric generators and the propulsion systems. This provides practically unlimited submerged endurance, which depends only on the food supplies for the crew. The S9G reactor on American Virginia-class submarines puts out about 40,000 shaft horsepower. Its reactor core has a lifespan of 33 years without refueling. With this reactor, the submarine maintains a submerged speed of over 25 knots. Alternative propulsion systems, like pump jets, improve stealth. They enclose the propeller inside a special duct to suppress cavitation. Cavitation is the process where vapor bubbles form and collapse, which creates a lot of noise. Pump jets cut this noise down significantly compared to open propellers and make the boat quieter at high speeds. At the same time, they are attached to the stern shafts, just like classic propellers. Submarines are equipped with a variety of offensive and defensive weapons for combat both underwater and on the surface. Most of these are launched from dedicated tubes or vertical launch systems built into the hull. The main weapon against other submarines and surface ships are torpedoes. Meanwhile, strategic and tactical missiles provide the ability to strike targets at long ranges. For defense, they use mines to block off waterways, as well as decoys to evade attacks. All these weapons work together with sensor data, which guarantees high accuracy during submerged operations. Torpedoes are the backbone of a submarine's arsenal. They are versatile weapons for taking out enemy ships at short and medium ranges. For example, the Mark 48 heavyweight torpedo is the standard for the United States Navy. It is initially wire-guided, and in its final stage, it switches on active acoustic homing using a complex sonar system. Its fully digital control system allows for software updates to handle new missions. It carries a 650-pound high-explosive warhead and accelerates to speeds of over 50 knots. Its range exceeds 30 nautical miles depending on the configuration. Usually, submarines have between 4 and 8 21-inch bow torpedo tubes, which allows for rapid salvo firing. For instance, Seawolf-class submarines have 8 tubes, while the Virginia-class has 4. These torpedoes can be launched from all classes of submarines, making them the primary tool for engaging both submerged and surface targets. Missiles expand submarine firepower to strategic scales. They are launched from either torpedo tubes or dedicated vertical launch systems. Submarine-launched ballistic missiles, such as the Trident II-D5, which arm Ohio-class submarines, provide nuclear deterrence. Their range is 4,000 nautical miles. They carry multiple independently targetable warheads of the W-76 or W-88 models. Each Ohio-class submarine carries up to 20 of these missiles in dedicated silos, providing global coverage. For non-nuclear strikes, cruise missiles are used, such as the Tomahawk Block 5. They are launched from torpedo tubes or vertical launch systems. These missiles fly at subsonic speeds, hugging the terrain, and can hit land targets with high precision at a distance of about 1,000 nautical miles. Such systems allow submarines to project power without ever having to surface. Mines and decoys are used to protect and blockade areas. They are covertly deployed through torpedo tubes. For example, the Captor Mark 60 mine is an encapsulated torpedo system. It is lowered to the seafloor, where it stays in standby mode until activated by acoustic or magnetic signals. After that, it launches a Mark 46 torpedo at an enemy submarine. The detection radius is about 2 miles. Submarines lay them in strategically important choke points, taking up to several dozen of these mines on a mission. To protect against enemy torpedoes, towed decoys are used, such as the AN/SLQ-25 variants. They are deployed behind the submarine and emit acoustic signals to attract and distract homing weapons. They often work together with the boat's propulsion system for maximum evasion effectiveness. These countermeasures are vital for survival in dangerous waters. The evolution of submarine weapons reflects progress in guidance systems, propulsion, and destructive power, from the simplest designs to high-speed precision systems. During World War II, torpedoes relied on magnetic detonators that triggered near the hulls of ships. This was more reliable than conventional contact fuses, but still depended on environmental factors. Post-war developments brought wire guidance and acoustic homing, like in the Mark 48 series, which significantly improved accuracy against actively maneuvering targets. Modern innovations include supercavitating torpedoes, such as the Russian VA-111 Shkval. They use gas bubbles to reduce water drag, reaching speeds of over 200 knots for rapid interception. However, this comes at the cost of higher noise levels and a shorter effective range compared to classic torpedoes. These advancements prioritize stealth, autonomy, and integration with sensor systems to counter modern threats. Submarines rely on advanced sensors and detection systems to identify threats, navigate underwater, and gather intelligence while remaining undetected. To do this, they use acoustic, optical, and electromagnetic technologies. This allows them to find surface ships, other submarines, mines, and seafloor features without giving away their own position. The main components of these systems are sonar for underwater detection, optronic masts for surface observation, and electronic support measures for intercepting signals. Sonar remains the foundation of detection. It can be active or passive. Active sonar emits sound pulses and records their echoes bouncing off targets. This makes it possible to accurately determine the distance and type of objects at ranges reaching dozens of miles, although the exact range depends on environmental conditions and the size of the target itself. Passive sonar, on the other hand, operates silently. It uses hydrophone arrays purely to listen to the ocean, picking up ambient noise, propeller cavitation, or the mechanical sounds of other vessels. This makes it the perfect tool for stealth operations against a quiet enemy. Passive sonar often operates across broad frequencies to cover a wide spectrum of sounds and better identify targets. To monitor the surrounding space, Modern submarines have flank arrays. These are hydrophone sensors mounted along the sides of the hull. They provide passive detection in a full 360 degrees, supplementing the bow systems and improving situational awareness during maneuvers. Today, traditional optical periscopes have mostly been replaced by photonics or optronic masts. Emerging after the 1990s, they allow observation through fiber optics without penetrating the submarine's pressure hull. This technology was first tested on the submarine USS Memphis in 1992. These masts are equipped with high-resolution digital cameras for both visible and infrared spectrums, as well as laser rangefinders. They feed a digital 360-degree panoramic view directly into the control room, maintaining the integrity of the hull. This shift increases the survivability of the boat, provides enhanced and stabilized imagery, and allows for integration with combat systems, just like on the Virginia-class submarines. Electronic support measure systems passively detect and analyze electromagnetic emissions to identify threats. Their receivers intercept radar signals from surface ships or aircraft. By analyzing the frequency, pulse width, and modulation, the system classifies the emission sources and pinpoints their location across a full 360 degrees. For submarines, there are compact systems like the ES-361U. They provide high sensitivity in the 2 to 18 gigahertz range and can simultaneously track hundreds of emission sources, instantly assessing the threat level. Among the latest developments are synthetic aperture sonars for high-precision seabed mapping, along with laser scanning systems for mine hunting. These sonars combine the echoes from multiple pulses along the course of the submarine. This makes it possible to get seabed images accurate to within a few inches to find hazards, geological features, or hidden objects. For example, similar mine hunting systems successfully operate at depths of around 2,000 feet. In addition to this, laser scanning technologies used in towed mine hunters like the AN-AQS-20C project light underwater. This creates detailed three-dimensional profiles of mines near the surface or on the bottom, allowing them to be quickly classified during operations. All these systems work closely with navigation, giving the crew the most complete picture possible of the underwater environment. Submarines rely on inertial navigation systems with ring laser or fiber optic gyroscopes to accurately determine their location without surfacing. They combine accelerometers and gyroscopes to track acceleration and orientation. In modern systems, the margin of error is less than 1 mile per day. This allows the boat to stay submerged for long periods with minimal course deviation. To correct these deviations, submarines deploy special buoys. They float to the surface, catch a GPS signal, and transmit the coordinates back via an acoustic or wire link. Meanwhile, the boat itself can remain submerged at depths of up to 820 feet. While submerged, Doppler velocity logs measure speed relative to the seabed. They emit acoustic pulses and analyze their echoes. This aids in navigation when a bottom lock can be achieved at depths of up to 10,000 feet. Communicating with submerged submarines is tricky because seawater really messes with high-frequency radio signals. So, for one-way transmissions of orders from shore, they use very low-frequency radio waves, typically in the range of 3 to 30 kilohertz. These waves can penetrate the water down to about 65 to 130 feet. They can send a signal over a distance of 60 to 620 miles, depending on how powerful the transmitter is and how conductive the ocean water is. For communication at even greater depths, they use extremely low frequencies, from 3 to 300 hertz. These can reach over 1,000 feet down to deliver short-coded messages. This requires massive shore-based antennas, similar to the former American Project ELF system. These methods are great for keeping a submarine's position secret. However, the data transfer rate is so slow it only allows for sending the most critical commands, not voice messages or large files. Life support systems keep the crew going during long missions underwater. They generate oxygen by splitting fresh water molecules through electrolysis. This process typically produces about 3 to 4.5 pounds of oxygen per crew member daily, while a person only needs around 2 pounds to breathe. Carbon dioxide is removed using special filters containing lithium hydroxide. This chemical absorbs the gas. Emergency canisters can soak up about 3/4 of a pound of carbon dioxide for every pound of lithium hydroxide before needing to be replaced. Water and food supplies are usually sufficient for patrols lasting up to 90 days. Drinking water comes from desalinated seawater and recycled condensation. The crew relies on shelf-stable and canned foods to minimize waste. If a patrol has to be extended, strict rationing becomes necessary. Onboard atmosphere control includes dehumidifiers that maintain humidity below 70%. They also use chemical deodorizers to neutralize odors. Combined with ventilation, these systems prevent condensation and the growth of microbes. In case of an emergency, there are special escape suits. These suits have a hood with an oxygen supply, allowing for a safe ascent from depths of up to 600 feet. The suit not only helps a person float, but also protects them from the cold. Attack submarines, which the United States Navy designates as SSNs, are built primarily to hunt and sink enemy submarines. They can also engage surface ships with torpedoes. Additionally, these boats are used for literal combat operations. From hidden submerged positions, they can launch Tomahawk cruise missiles, delivering surprise attacks against land targets. During large-scale fleet operations, attack submarines are vital for protecting carrier strike groups. They establish an invisible defensive perimeter, constantly monitoring the depths and reacting instantly to any detected threat. Ballistic missile submarines form the sea-based component of the nuclear triad. They ensure our second strike capability thanks to missiles equipped with multiple warheads. Their sea patrols average about 77 days, after which they spend roughly 35 days in port for maintenance. This operational tempo allows them to maintain a constant deterrent presence while remaining undetected. Over time, submarine tactics evolved from coordinated group attacks to highly sophisticated stealth operations. During World War II, German U-boats in the Atlantic employed wolf-pack tactics. Groups of 8 to 20 submarines would position themselves to locate enemy convoys and then attack them with massive torpedo salvos. Later, American forces in the Pacific adopted similar strategies. Today, the main emphasis is on stealthy ambushes. Individual submarines utilize noise reduction systems and passive sonar to lie in wait and strike high-value targets. For defense, layered strategies are employed. For instance, sensor networks are deployed on the ocean floor. These passive microphones function as an early warning system, helping submarine hunters detect targets. Modern submarines are increasingly becoming tools of hybrid warfare. They combine conventional strikes with covert sabotage, such as destroying underwater infrastructure. Countries like Russia and China have already shown that their specialized submarines can attack undersea cables. Over 95% of global internet traffic passes through these cables. Damaging them could cause massive economic and communication problems without firing a single shot. During World War I, German U-boats waged unrestricted submarine warfare. They sank Allied merchant and passenger vessels to cut off supply lines. One of the most famous incidents happened on May 7, 1915. Then, the German U-boat U-47 torpedoed the British ocean liner Lusitania off the coast of Ireland. The vessel went to the bottom in just 18 minutes. Out of 1,959 passengers and crew members, 1,198 people died, including 128 Americans. This caused massive outrage and shifted public opinion in the United States, ultimately leading to their entry into the war in 1917. In World War II, submarines played a key role for both sides. German U-boats inflicted heavy losses on Allied convoys until they improved their anti-submarine defenses. After the war, the Royal Navy carried out a massive operation called Deadlight. From November 1945 to February 1946, 116 surrendered German U-boats, mostly Type 7 and Type 9 models, were scuttled in the North Atlantic, northwest of Ireland. This was done to keep them out of the hands of potential enemies and to fulfill disarmament agreements. The U-boats were towed to designated areas where they were blown up or simply had their sea valves opened. This put an end to the threat of German U-boats, which had sent over 3,000 Allied ships to the bottom during the war years. Another major Allied success was the sinking of the Japanese aircraft carrier Shinano on November 29, 1944. The American submarine Archerfish spotted it in the Pacific Ocean about 200 miles east of Honshu. Shinano, which was originally built as a Yamato-class battleship but converted into an aircraft carrier, had a displacement of 59,000 tons. At the time, it was the largest aircraft carrier in the world. Archerfish fired 6 torpedoes, and at least 4 of them hit the target. The vessel sank in 7 hours, taking the lives of over 1,000 Japanese sailors. This battle clearly demonstrated how effectively American submarines destroyed the most important ships of the Japanese fleet at the end of the war. During the Cold War, submarines became the backbone of nuclear deterrence. But a few incidents showed just how dangerous underwater standoffs could be. On October 3, 1986, disaster struck the Soviet Yankee-class nuclear submarine K-19. While patrolling the Atlantic Ocean, about 600 miles east of Bermuda, a fire broke out in a missile tube and caused an explosion. This led to reactor instability and the risk of a partial meltdown. The crew fought the fire for 3 days. Seaman Sergei Preminin sacrificed himself to manually shut down the reactor. On October 6th, the submarine sank, taking the lives of 6 crew members. This tragedy exposed serious flaws in the design and management of Soviet submarines. Another tense standoff happened during the Cuban Missile Crisis. On October 27, 1962, U.S. naval forces hunted 4 Soviet Foxtrot-class submarines in the Sargasso Sea. Among them was B-59. American ships were dropping depth charges, and Soviet captain Valentin Savitsky decided that war had already begun. He ordered a 10-kiloton nuclear torpedo to be prepared for launch. However, his second-in-command and political officer, Vasily Arkhipov, overrode his decision. This saved the world from nuclear escalation. This incident clearly showed just how high the stakes were in the underwater game between superpowers. In more modern history, submarine losses exposed major issues with their maintenance and rescue operations. On August 12, 2000, the Russian Oscar II-class submarine Kursk, or K-141, sank during exercises in the Barents Sea. The explosion of a faulty torpedo triggered a chain reaction. All 118 crew members died, even though some sailors survived the initial blast in the aft compartments. The rescue operation was derailed by constant delays and equipment failures. When the hull was raised to the surface in 2001, notes from the trapped sailors were found inside. A similar tragedy occurred on November 15, 2017. The Argentine TR-1700 class diesel-electric submarine San Juan exploded underwater off the coast of Patagonia. The likely cause was a short circuit from flooding in the battery compartment. All 44 crew members died. In 2018, the wreckage of the boat was found at a depth of 2,976 feet. Today, geopolitics is changing the rules of the game once again. In 2021, Australia, the United Kingdom, and the United States formed the AUKUS Security Pact. Under this agreement, Australia will get nuclear-powered submarines to boost defense in the Indo-Pacific region. The countries agreed to share technology to build submarines with nuclear propulsion but conventional weapons. They will be based on the American Virginia-class and the British Astute-class submarines. This will strengthen joint maritime security without violating nuclear non-proliferation agreements. The Submarine Rotational Force West mission is already scheduled to begin in 2027. It involves regular rotations of American Virginia-class submarines in Australia. This will help the fleets work better together, increase the Allied underwater presence, and fundamentally change the naval balance of power in the region. Submarines have played a key role in the development of oceanography. They allowed scientists to observe the ocean depths firsthand and collect samples where regular surface ships just cannot reach. One of the very first and most famous research submersibles was Alvin, launched in 1964 by the Woods Hole Oceanographic Institution. This submersible could reach a diving depth of up to 21,300 feet and accommodated a crew of 3. In 1986, Alvin made a dive to the wreck of the Titanic at a depth of around 12,500 feet. The samples and photographs collected then helped us understand how objects are preserved at great depths and how microorganisms work down there. The Soviet Mir research submarines, built by the Institute of Oceanology in 1987, played a similar role. Since the late 1980s, they explored hydrothermal vents, particularly along the mid-Atlantic ridge, discovering unique ecosystems that exist thanks to geothermal energy. Throughout its history, Alvin completed over 5,000 dives, and the Mir submersibles completed hundreds, taking thousands of scientists to the bottom to study phenomena that would otherwise remain out of reach. Research submarines do incredibly important work. They map the seafloor, study the diversity of life, and collect climate data. As of 2020, over 80% of the global ocean remained unmapped with high precision. Vessels like Alvin and Mir used sonar and cameras to create detailed maps, discovering seamounts and trenches that affect ocean currents. By June 2025, according to the Seabed 2030 project, about 73% of the seafloor remains unexplored. To study deep-sea life, these vessels use robotic arms. They collect samples from extreme depths, allowing scientists to examine creatures that have adapted to immense pressure and total darkness. In climate research, submarines measure acidity and carbon levels in the water. This helps us understand how the ocean absorbs atmospheric carbon dioxide, which accounts for about 25% of human emissions, and how that impacts marine ecosystems. The development of autonomous technology has vastly expanded the possibilities of science. Now, large-scale surveys can be conducted without humans on board. Autonomous underwater vehicles of the Remus series, developed by that same Woods Hole institution, can carry out long-endurance missions and cover distances up to 62 nautical miles. They use multi-beam sonar for accurate seafloor mapping and environmental monitoring. They are complemented by crewed submarines like the Chinese Jiaolong. In 2012, it descended to the bottom of the Mariana Trench to a diving depth of 23,170 feet. Down there, it collected geological and biological samples so scientists could study tectonic processes and extreme life forms. Technologies like these allow for systematic research with a level of precision simply unavailable to standard surface ships. The impact of these studies is hard to overstate because they completely change our understanding of the marine environment. For example, in 2023, expeditions by the United States National Oceanic and Atmospheric Administration used submarines to discover countless new deep-sea species. Among them were previously unknown corals and sponges in Alaskan waters. This greatly expanded our knowledge about areas with the highest biodiversity and their role in storing carbon. These discoveries prove once again just how vital submarine technology is for understanding the hidden life of our ocean. Civilian and commercial use of submarines mainly involves tourism, industrial inspections, salvage operations, and marine infrastructure maintenance. This differs significantly from military or scientific missions. For these commercial tasks, usually in coastal or shallow waters, both manned vessels and remotely operated vehicles are used. For example, the company Atlantis Submarines, founded in 1985, pioneered submarine tourism. It conducts tours in Hawaii. Their submarines, like Atlantis 14, dive to a depth of about 100 feet and hold up to 64 passengers, who can comfortably observe coral reefs and marine life. In the commercial sector, submarines and underwater vehicles inspect pipelines for corrosion, leaks, or damage. This eliminates the need for divers, making work in the oil and gas industry safer and more efficient. Salvage operations, specifically the recovery of sunken ships or wreckage, also require this kind of equipment. However, this involves high risks. A tragic example was the implosion of the submersible Titan in 2023 during a commercial expedition to the Titanic wreckage. At that time, 5 people died due to the destruction of the pressure hull under immense pressure. The United States Coast Guard investigation revealed avoidable engineering mistakes. This highlighted the need for strict safety regulations for non-military operations. After this, in 2025, standards were updated, with a special emphasis on enhanced pressure testing for tourist and salvage vessels. Commercial underwater vehicles are also actively used in the open ocean. They help maintain oil platforms and lay submarine cables where remotely operated robots place fiber optic lines on the sea floor. In early 2025, The global market for autonomous and remotely operated underwater vehicles was valued at roughly $3 billion. This growth is driven by the massive needs of the energy and telecommunications infrastructure. Regulations for civilian submarines differ from military standards. The main focus here is on passenger safety during tours rather than combat readiness. The International Maritime Organization sets key requirements for the design, construction, and operation of passenger vessels. These cover hull strength, life support systems, and emergency procedures, which are ideally adapted for tourist and short commercial dives. These regulations clearly define authorized depths and seafloor limits to minimize risks. Submarines operating in polar regions require special preparation. They have to avoid the dangers created by sea ice. For example, massive ice keels reaching deep underwater can damage the vessel while surfacing or underway. To reduce this risk, submarines use upward-looking sonar. They measure the underside of the ice, find thinner areas suitable for safe surfacing, and plot a course beneath the thick ice canopy. The data collected during such Arctic transits give the crew accurate information about the ice thickness. This allows them to avoid collisions while remaining completely undetected. A landmark demonstration of submarine capabilities under the ice took place in 1958. That was when the submarine USS Nautilus made the first submerged transit to the North Pole. The boat traveled 1,830 nautical miles under the Arctic ice cap from Point Barrow in Alaska to the very top of the world. Setting out on July 23rd and submerging on August 1st, Nautilus crossed the geographic North Pole on August 3rd. The crew had to navigate through difficult ice conditions, relying on dead reckoning and early inertial navigation systems. On August 7th, the submarine successfully surfaced off the coast of Greenland. This operation proved that extended under-ice expeditions were entirely possible when using nuclear propulsion, which allows vessels to operate submerged for long periods without having to surface for air. At depths greater than 19,680 feet, submersibles and submarines require incredibly strong pressure hulls. They are made from high-strength materials like titanium alloys. This is necessary to withstand hydrostatic pressure reaching 600 atmospheres and prevent structural failure. These hulls often have a spherical shape to distribute the load evenly. Because of this, they can operate across 98% of the ocean floor. Their design combines minimal weight with high resistance to colossal pressure. This is exactly what allows for precise control of diving and surfacing in places like the Mariana Trench. A great example of deep-sea pressure resistance was the bathyscaphe Trieste in 1960. It reached the Challenger Deep at a depth of 35,814 feet. This is the deepest known point in the ocean, where the pressure exceeds 1,000 atmospheres. On January 23rd, piloted by Jacques Piccard and Don Walsh, the reinforced steel sphere of the vessel withstood a dive lasting over 5 hours. This allowed for brief observations on the bottom before surfacing. This manned dive proved that humans could safely explore the ocean even at extreme depths. Extreme conditions challenge more than just structural strength. For instance, in the water column, there are thermal layers with different levels of salinity. They refract sonar signals and create what are called acoustic shadows, which makes navigation and detecting other objects very difficult for submarines. And in tropical waters, due to the large number of marine organisms, hulls quickly become covered with biofilms and barnacles. This increases hydrodynamic drag by 40% and significantly raises fuel consumption. Therefore, to maintain maneuverability, submarines require frequent cleaning. By 2025, the accelerated melting of Arctic ice has opened up access for submarines to previously impassable areas. The sea ice extent has dropped to record lows, specifically during its annual maximum on March 22nd. This has expanded navigation windows and reduced risks during under-ice transits. These changes, driven by warming that is twice the global average, make extended operations in the Arctic basin much easier. However, new threats are also emerging, such as the unpredictable movement of ice flows. At the same time, deep submergence vehicles are helping to study the ice shelves of Antarctica. For example, in 2024, the autonomous underwater vehicle RAN explored the underside of the Dotson ice shelf, which is 1,148 feet thick. The vehicle discovered teardrop-shaped ice formations and scour marks from currents, helping scientists better understand glacier dynamics. A submarine crew typically consists of 100 to 150 people, depending on the class of the boat and the combat mission. For example, the United States Navy Virginia-class attack submarines have a crew of 145 people, including 17 officers and 128 enlisted sailors. The main roles are filled by commanding officers and executive officers, who are responsible for leadership and navigation. There are also nuclear reactor specialists who operate the propulsion systems, sonar technicians who monitor the underwater environment, as well as weapons officers and damage control experts. To maintain continuous operation, the crew stands watch in shifts. Traditionally, this is a cycle of 6 hours on watch and 12 hours off. However, since 2015, some American submarines have switched to a schedule of 8 hours on and 16 hours off. This helps them better align with biological rhythms and maintain alertness. Submariner training is extremely rigorous and highly specialized. The main focus is on technical mastery, combat skills, and the ability to endure long periods in a confined space. Sailors who will work with nuclear systems study for about 6 months at the Nuclear Power School. There they study reactor theory, thermodynamics, and electrical systems before going through practical training on operating reactor prototypes. Officers and other specialists undergo additional training at facilities like the Naval Submarine School in Groton, Connecticut. The training includes dives and simulators where they practice emergency procedures and underwater navigation. An important part is psychological screening. Candidates are tested on their ability to withstand isolation by evaluating their tendency for claustrophobia, stress tolerance, and overall psychological condition. In recent decades, the composition of submarine crews has become more diverse, especially concerning the inclusion of women. In 2010, the United States Navy lifted the ban on women serving on submarines. The first female officers qualified and deployed in 2011, and enlisted women joined them in 2016. As of 2024, about 712 women were serving in the submarine force. This is less than 5% of the total force of 15,000 service members. However, the Navy plans to increase the percentage of women in mixed-gender crews to at least 20% to meet personnel and operational needs. Recent milestones include the appointment of the first female executive officer on an American submarine in 2022 and the first female chief of the boat that same year. And in September 2024, they commissioned the USS New Jersey. This is the first Virginia-class submarine designed from the start for fully mixed-gender crews. It's expected that the first female submarine commanding officer will be appointed by 2028. Changes are also taking place around the world. In 2020, Japan admitted its first female submariner to the National Naval Academy. This became a step toward openness amid a personnel shortage in the Japan Maritime Self-Defense Force. Ethnic diversity statistics vary by country, but integration programs have expanded recruitment, drawing in different demographic groups. This helps bring together different perspectives in high-risk environments. Forming mixed crews creates certain challenges. Specifically, they have to deal with claustrophobia, which is aggravated by the tight quarters of a submarine and prolonged isolation. Psychological tests thoroughly screen for claustrophobic tendencies because research shows that even trained professionals can experience severe anxiety in enclosed spaces under high pressure with no sunlight and no quick way out. In mixed crews, teamwork can be complicated by a lack of personal space and interpersonal conflicts. Early integration reports mentioned issues with sleeping arrangements and cultural adaptation, but over time, clear rules helped resolve most of these issues. These challenges highlight the need for ongoing training in conflict resolution and psychological resilience. This is the only way to maintain team unity during long patrols. Submarine crews face unique challenges during long submerged patrols where space is extremely limited. On older vessels, beds had a steel frame with springs, mattresses, and minimal overhead clearance. But modern designs, like the Virginia-class submarines, offer better conditions. Individual beds provide more privacy and comfort, completely eliminating the need for hot bunking. The galley, which often serves as a dining and recreation area, provides 3 full meals a day made from high-quality ingredients, although limited refrigerator space affects the availability of fresh food and crew morale during long missions. Noise and vibration continue to affect daily life aboard submarines. To reduce this impact and maintain crew performance, engineers strictly follow design standards for living quarters. These conditions are closely tied to life support systems, where an artificial atmosphere helps them survive but requires constant monitoring of the crew's health. Among the medical risks for submariners is radiation exposure from nuclear reactors. Under federal standards, the limit is 5 rem per year for the whole body, and below this threshold, no adverse effects are expected. Psychological stress is very common due to isolation and confined spaces. Studies of crews after accidents show that post-traumatic stress disorder occurs in 19% of sailors and adjustment disorders in 31% just 7 weeks after an incident. A lack of sunlight causes vitamin D deficiency. This prompted testing of full-spectrum lamps that simulate natural ultraviolet light. However, these lamps failed to completely stop the drop in vitamin D levels in the body over 6 weeks, even though the sailors themselves reported feeling somewhat better. In emergency situations, a quick response is key to saving the integrity of the vessel and the lives of the crew. During damage control drills, sailors practice controlling water intake using bilge pumps, closing watertight doors, and isolating breaches. This is done regularly so the crew can eliminate a threat in a matter of minutes. For rescues, they use the Deep Submergence Rescue Vehicle, or DSRV, which served until 2008. It could evacuate up to 24 people from a depth of over 2,000 feet by mating with the escape trunks. Modern systems, like the Submarine Rescue Diving and Recompression System, or SRDRS, continue to perform these tasks using mobile modules for reconnaissance and transport. Escape protocols are the last resort for shallow depths of up to 600 feet. Sailors use escape trunks and put on special SEIE immersion suits. These are pressurized suits that provide buoyancy and thermal protection during the ascent. On the surface, a built-in life raft deploys from the suit, keeping the person afloat and protected from the weather until help arrives. During World War II, crews had instructions to scuttle their vessels. If abandoning ship was inevitable, sailors opened the sea valves or used explosives to intentionally send the submarine to the bottom and keep it out of enemy hands. Since the year 2000, advances in submarine stealth technology have focused on making vessels quieter. Engineers use new materials and advanced hydrodynamic designs to minimize detection by sonar systems. For example, anechoic tiles applied to the hull absorb a massive portion of incoming sonar waves. Advanced metamaterial coatings can absorb over 91% of sound energy while reflecting less than 3%. This distorts return signals and greatly increases the submarine's chances of surviving active sonar sweeps. These tiles are usually made from rubber or synthetic polymers and are less than 2.7 inches thick. They also block the noise coming from internal machinery, making the whole submarine much quieter. To add to this, highly skewed propellers with up to 7 blades have become the standard for modern designs. They spin at lower speeds to reduce cavitation and broad background noise. Studies confirm that these propellers lower hydrodynamic sound by keeping pressure steady in the water behind the submarine. In 2024, China introduced an X-stern design on its Type 041 Zhou-class nuclear attack submarine. This setup improves maneuverability and reduces the acoustic signature. It significantly drops the speed of the propeller wake, improving propulsion efficiency by over 7%, which makes it much harder for adversaries to track the submarine through wake detection. However, this prototype actually sank during construction in 2024, causing a major setback for the program. The Virginia-class submarines are a perfect example of these modern stealth standards. They produce radiated noise levels of around 95 decibels at speeds of 5 knots. This is basically the same as the natural background noise of the ocean, making them significantly quieter than older classes and allowing them to operate in contested waters with very little risk of being picked up by passive sonar. Autonomous technology has also advanced massively through unmanned underwater vehicles, which provide constant surveillance without putting human crews at risk. The Boeing Orca, an extra-large unmanned vehicle contracted in 2019, has a range of up to 6,500 nautical miles at a standard speed of 3 knots. It easily supports long-term missions like anti-submarine warfare and payload delivery. Integrated artificial intelligence takes this a step further by improving target recognition. Deep learning algorithms on autonomous underwater vehicles allow them to identify underwater threats in real time, a feature already tested in United States Navy programs for automated undersea warfare. Swarms of these unmanned vehicles greatly improve mine hunting capabilities. Coordinated groups of small drones, like those being developed in European experiments, can efficiently cover massive areas. They use spread-out sensors to detect and clear mines, keeping manned ships completely out of danger. Combining manned and unmanned systems is a major evolution in naval warfare. These hybrid operations use the strengths of both to protect crews in high-threat environments. Submarines can easily deploy and recover drones, like the L-3 Harris-Ivor series, while completely submerged. This extends their sensor networks for intelligence and surveillance without ever needing to surface. The United States Navy's hybrid fleet concept, which includes platforms like the Orca, aims to share tasks between manned submarines and autonomous vehicles, improving both operational speed and survivability. Ongoing DARPA projects, including the positioning system for deep ocean navigation, use AI for highly precise undersea travel. By relying on quantum sensors and inertial systems, these unmanned vehicles can maintain their exact location without GPS in denied areas, a capability successfully shown in 2025 demonstrations. Submarines create a few environmental issues, mostly from the pollution of sunken ships and the noise they make while running. Over 200 World War II-era submarines rest on ocean floors around the world. Many of them are leaking oil and dangerous chemicals from their electrical gear and paint, which pollutes the surrounding sand and marine life. For example, the wreck of the Japanese submarine tender Rio de Janeiro Maru in the Chuuk Lagoon is still leaking fuel oil. This threatens coral reefs and fishing areas in the Pacific. On top of that, the engines of active submarines create underwater noise that bothers marine mammals. This noise interferes with whale migration by blocking their communication and causing them to get confused or delayed. Studies show that loud noises can slow down humpback whales when they are looking for food and push them off course during their journeys. Navies are trying to make submarine operations more environmentally friendly by testing biofuels in diesel submarines and improving how they handle nuclear waste. The United States Navy has tested 100% renewable diesel in marine engines. This proved it works well with existing systems and could help lower carbon emissions in non-nuclear submarines. For nuclear submarines, strict recycling programs take apart retired hulls, fix up reusable parts, and safely seal reactor compartments to prevent any radioactive waste from escaping. New technology in air-independent propulsion systems, like those using hydrogen or ammonia fuel cells, also helps cut down on emissions. These systems allow submarines to stay submerged much longer without needing to surface for air. Climate change makes these environmental issues even worse, especially with melting Arctic ice and rising sea levels. By the year 2025, faster warming in the Arctic has changed how sound travels underwater because of shifting temperature layers. This can actually make it easier to detect submarines by carrying acoustic signals over much greater distances. Rising sea levels also threaten to flood parts of coastal naval bases. This puts critical infrastructure for submarine maintenance and deployment in danger, with places like Naval Submarine Base Kings Bay at risk of flooding that could hurt their readiness. International agreements try to address these impacts. The United Nations Convention on the Law of the Sea from 1982 requires countries to prevent marine pollution from seabed activities. This includes rules against damaging the ocean floor through submarine operations or by disturbing sunken wrecks. Part 12 of this agreement focuses on protecting the marine environment and encourages countries to work together to reduce pollution from ships and facilities. The spread of advanced submarine technology has increased geopolitical tensions, especially in the Indo-Pacific region. In September 2021, the United States, the United Kingdom, and Australia announced the AUKUS partnership. This security agreement allows Australia to acquire nuclear-powered submarines through shared technology and joint development. It is the first time this kind of technology has been provided to a non-nuclear weapons state under the Nuclear Non-Proliferation Treaty. The goal is to build a stronger defense against regional threats, though it has sparked some concerns about keeping nuclear technology secure. At the same time, the Chinese Navy is expected to grow its submarine force to about 80 vessels by the year 2035. This includes advanced nuclear-powered attack and ballistic missile submarines. It is part of a massive naval upgrade that could reach 435 ships in total by 2030. International treaties play a key role in keeping submarine nuclear arsenals in check. The Strategic Arms Reduction Treaty, signed in 2010 and entering into force in 2011, sets clear limits for the United States and Russia. Each country can have no more than 700 deployed intercontinental ballistic missiles, submarine-launched ballistic missiles, and heavy bombers. The total number of strategic nuclear warheads is capped at 1,550. This agreement promotes strategic stability by significantly reducing the nuclear threat from under the sea. However, it is set to expire in February 2026, and this is happening against a backdrop of serious geopolitical tension. When it comes to nuclear non-proliferation, the International Atomic Energy Agency strictly controls the transfer of nuclear propulsion technology. This applies to building new fleets too, like under the AUKUS alliance. The main goal here is to guarantee that the technology will not be used to build new weapons. At the same time, conventionally armed, nuclear-powered submarines themselves do not violate any international agreements. Looking ahead, emerging technologies will completely change the game underwater and drive strategic competition even further. The United States Navy is actively working on integrating hypersonic missiles capable of flying at speeds over Mach 5. By the late 2020s, the plan is to deploy them on Virginia-class attack submarines, as well as adapt Ohio-class submarines for this role. This will allow for lightning-fast strikes against high-value targets. Another revolutionary innovation is quantum sensors. They will provide ultra-precise threat detection and navigation with absolutely no need to surface. It is expected that by 2040, unmanned vehicles will dominate submarine fleets. They will completely take over reconnaissance, mine clearance, and strike missions, significantly reducing the risks to human crews. The future really belongs to scalable autonomous systems that will gradually phase out traditional manned submarines. Export markets and regional arms races only confirm these trends. The French Scorpène-class diesel-electric submarines are in massive demand globally. They are being bought by Brazil, which has commissioned 2 boats since 2022 and is building 2 more, as well as by India, which has 6 of these submarines under construction, along with Malaysia and Chile. Technology transfers and local production are significantly strengthening the naval forces of these countries. This proliferation of technology is leading to a rapid escalation of the underwater arms race in the Indo-Pacific region. The AUKUS alliance is deterring China's naval expansion, which in turn is pushing countries like Indonesia and Japan to urgently modernize their fleets amidst growing tensions at sea.